In this lecture, we talk about initial value problems for differential equations. So, initial value problems. So, they are differential equations like first order and second order. So, I'm starting with first order. Dy by dt equal to f of ty with one condition. When t equal to t naught, we know the solution which is y naught. So initially we know the solution, and this is called initial condition. Okay, so together differential equation with plus one condition, we say these are initial value problems. So they originate in many applications. For example, there is a famous population growth model. So population of any individual is denoted by NT, and its rate change in population is proportional to itself, population. So from this you got dn by dt equal to n, and let us say initially when t equal to 0, we know, let us say 10,000 peoples are there initially. Okay, so also there would be a constant of proportionality, and of course this is differential equation with one condition. So this is initial value problem, and you can solve it directly, like this is variable separable form. So I can write it dn by n equal to k times n, and on integrating you got log n equal to e power, dn by n equal to k times dt. So log n equal to kt plus some constant, you can write log c. So n equal to c e power kt, and initially when t equal to 0, population is 10,000. So from this you got 10,000 equal to c e power 0, that is 1. So c is 10,000. Okay, so we have nt equal to 10,000 e power kt. So this is the solution that we already studied in calculus. This is called exact solution of initial value problem. But this is not always possible. That, for example, you have a equation like dy by dt equal to e power minus t square, let us say with one condition. So usually integration of such kind of functions or all functions is not always possible. So we will look for numerical solutions, and likewise definite integral you can solve on computer. Similarly, you cannot solve only differential equation. Okay, so that is not possible, but we solve differential equation with one condition, that is called initial condition. And those, in those notations we have fty, that is e power minus t square, or let us say you have some another function log y. Okay, so these are initial value problems, and in this topic we talk about solution, or you can say numerical solutions of initial value problems. So this is the topic that we are going to study in this lecture. So I am writing a numerical solution of initial value problem. In short, I write IVP. Okay, so this is initial value problems. So we have dy by dt equal to right hand side, which is denoted by f, and with one condition. So solution means that this is my domain starting from t naught. So I divide my domain into small cells, and you can take equal gap h. Okay, so t1 is t naught plus h, t2 is t1 plus h, and so on. And initially I know the solution. At first point this is y0, I know. At second point I will write solution as y1, and at t2 I will write solution y2. Okay, so what is y1? Y1 means approximate solution that at t1, and so on. So and this is given, that I know from condition. At t0 solution is y0. So firstly, to write the solution I am writing integral form of initial value problems. So I integrate dy by dt equal to fty, and I am starting from t0, and I know solution, that is y0, and I am going to t1, which is t0 plus h, and solution at this point is denoted by y1. So we integrate dy, y changing from y0 to y1, and right hand side fty dt, t changing from t0 to t1, and integral of left hand side is just y, and upper limit minus lower limit. Integral of right hand side, that we will do. Okay, so from this we have y1 equal to y0 plus t0 to t fty dt. So I am putting this label I as integral form. So if integral of f right hand side is possible, as we have seen in that population example, okay, so integral is possible by separating variable. If integration is possible, you will get exact solution. But every continuous function is integrable, but we don't know how to integrate every function. Therefore we rely only for numerical techniques. So here I am writing approximation of this integral, and we will write different rules. Okay, and first approximation is that which is known as overcoming method, that is Euler's method. Euler's method. Okay, so this is named after Swiss mathematician Leonhard Euler. So this is the one of the simplest method to solve initial value problem, and there are many ways to derive it. I am writing from integral form. So I am writing that integral form again. So that is y1 equal to y0 integral t0 to t1 fty dt. Okay, and here I am taking approximation of f. Okay, so I am just calculating f at t0 y0, since we know the initial point. Okay, that is known, so we calculate this value at initial point which is given. So you can write this is approximately equal to, so y1 is y0. Now I know f at initial point, so I can take f outside from integral, and integral of dt will be t1 minus t0, and t1 minus t0 I can write this as h. Okay, t1 minus t0, t1 is t0 plus h, so this is just h. Okay, so this is first simple rule. This is called Euler's method. So I am starting from this point t0, so solution at t1 is given by y1. Now repeat the procedure. Okay, so go to next point t2, denote solution at by y2, and so on. So similarly you got y2, that will be y1 plus hf t1 y1, and so on. So in general I write it as, so what I am writing, ti plus 1 point, that is ti plus h, and solution at this point, solution at this ti plus 1 is denoted by yi plus 1, and this is just yi plus hf ti yi, and this is called Euler's method. Okay, and similarly you go further, so y2, y3, and you can calculate solution at different point by taking suitable or small h. Okay, and alternatively you can derive this method from Taylor series. That is important. So what I write Taylor series of any function about point A, so that is at fa plus h f dash a plus h square by 2 factorial f double dash at a, and so on. So this is an important series. Okay, so everything you know at a, right hand side is at a, fa, f dash a, second derivative, everything at a, and you are getting function value at near point a plus h, and by taking h inactive you can calculate here. Okay, and this information we apply here. So you know solution at one point and you can find solution at nearby point by writing Taylor series. Okay, so this is famous Taylor's series, and if you cut Taylor series at certain point, and that is called Taylor polynomial. Okay, so for Euler's method I write Taylor series up to two terms only. Okay, so what are two terms? So I am writing first yt1, that is y t naught plus h, next point, so that is y at t naught plus h y dash at t naught. Okay, so just stop here. So this will be approximate value, and y t naught, and this is I denote by y1, y t naught is y0 plus h, and this derivative from the equation dy by dt equal to f. Okay, so this is dy by dt, so f at initial point t naught y naught, and you got same equation, that is Euler's method. Okay, and here one important thing that we define from Taylor series, that is called order of method. Okay, so what is order of method? That I am going to define. So order of method, so we write Taylor series that I have written earlier, so you can write about any point ti plus 1, which is ti plus h, so this is y at ti, h y dash at ti, h square by 2 factorial y double dash at ti, and so on. So if I cut this series at first derivative, then I say this is first order method, and if I cut series at h scale second derivative, so I say that this is second order method, and so on. Okay, so what is order? So if I cut series, or you can say the neglected term, so if we cut Taylor series having term h power p, then order of method is p. So in Euler method we have truncated the series at first derivative, or in other words the error have minimum power h scale. Okay, so if error has power hp plus 1, then order of method is p. So that is the same thing I am saying. Okay, so from this you can say Euler's method has first order or it is a first order accurate. So Euler's method is a first order method. And similarly, if you write Taylor series up to h square, so that is second order method, and so on. So we will study first, second, third and fourth order method in this chapter, and in fact first, second and fourth order. So next method in this category, that is known as modified Euler's method. Modified Euler's method or improved Euler's method. You can derive this method from Taylor series by writing up to second derivative and then eliminate derivative on the right hand side. Okay, you can derive this also, but I am deriving it from the integral form I have written earlier, from this one. Okay, and in this integral form I have integration on the right hand side, and now I approximate this integral using trapezoidal rule that we have studied earlier. Okay, so apply trapezium or trapezoidal rule on right hand side, and that is our next method, modified Euler's method. So I am writing again integral form, that is y1 equal to y0 plus hf integral of f from t0 to t1. Okay, so apply, use trapezium rule on right hand side, trapezium rule for integration. So you got y0, and trapezium rule is h by 2. Okay, so function value at this point and this point, h by 2, function value at first point which is t0 y0, and second point t1 y1 and t1 y1. But here we have one difficulty here, that you don't know this y1. Okay, we have y1 in the right hand side, but we don't know, but still you can write it. So I am taking h inside and I am writing t1 as t0 plus h, and this y1 I am writing by Euler's method that we have written earlier. Okay, so y1 is y0 plus hf t0 y0. Okay, so use approximation of f, this y1, write y1 by Euler's method. Okay, so y1 by Euler's method on right hand side. And in modified Euler, now we used two notations. So this function value, first term I am writing with k1 and second term I am writing with k2. So these are just notations. So we denote k1 equal to first term hf t0 y0, and k2 is second term in bracket, that is, so this one. Okay, so that is hf t0 plus h y0 plus that is hf t0 y0. Okay, so this is just k1, so y0 plus k1. So now we have y1, that is y0 plus 1 by 2 k1 plus k2. Okay, so in general we have, and so on. So this is called modified Euler. So in general we write next point ti plus 1, that is ti plus h, and we calculate two number k1 that is at ith level, and k2 is ti plus h yi plus k1, and solution at ti plus 1, which is yi plus 1. So this is just yi plus 1 by 2 k1 plus k2, and this is called modified Euler's method. And you can also derive this method from Taylor series by writing up to second derivative, and hence it is second order accurate, or this method has order 2. Okay, so now I am taking examples of these methods, and then we will move to next category. And you should recall this integral form that will be used later on also. So take first example that says that you have initial value problem dy by dt plus 2y equal to 2 minus e power minus 4t, y at 0 equals to 1. So by taking h, that is also called step size h, 0.1, find solution at 0.1, 0.2 using Euler's method. Okay, so firstly I am writing the equation in standard form. Keep derivative on left hand side and take everything on right hand side. So this is my f function. y0 equal to 1 means initially t0 is 0, initially y is 1, and step size is 0.1, that is given. Okay, and you know solution at 0, and you need to find solution at 0.1 and 0.2 using this method, Euler's method. Okay, so now I write, calculate, take step size 0.1. So t1 is next point. So t1 is t0 plus h, that is 0.1, 0 plus 0.1, 0.1, and then you have y1. y1 means y at 0.1, which is y0 plus hf t0 y0. So y0 is 1 plus h is 0.1, 0 and 1. So in the formula of f, replace y with 1, minus 2y plus 2 minus e power minus 4t, t with 0, and solve it. This is 0.9. So solution at 0.1 is 0.9. This is first solution. Similarly, you write next point t2, this is t1 plus h. Okay, so 0.1 plus 0.1, this is 0.2, and solution at point 2, which is denoted by y2. So y2 is just y1 plus hf t1 y1. So y1 you computed 0.9, h is 0.1, f t1 is 0.1, y1 is 0.9. So in the formula of f, replace y with 0.9 and t with 0.1, and simplify with calculator. This is approximately 0.852967. Okay, so this is the solution at next point. Similarly, you can find solution at other points. Okay, let's take one more example, which says that we have initial value problem that is dy by dt equal to 2 by ty plus t square e power t, y1 equal to 0. Okay, so this is given. It says that use Euler's method to find solution at 0.1 and 0.2. Okay, oh sorry, not 0.1, I am starting with 1, so 1 at 1.1 and 1.2. Okay, with step size 0.1. Then it says that use these values that you compute and linear Lagrange interpolation to find solution at, let us say, 1.04. Okay, so firstly we solve it, then we will go to second part. So in notation I have dy by dt equal to 2 by t y plus t square e power t. So this is my f, and initially it is given that y1 equal to 0, so t naught is 1, y0 is 0, step size is 0.1. Okay, and then you can compute solution at next point t1, which is 1.1. so y1 means y at 1.1. I am starting with 1. Okay, 1 is the starting point, so that is y0 plus hf t0 y0. So y0 0, h is 0.1, f is t0 1, y0 0. So in this formula f 2 by ty, replace t with 1 and y with 0. Okay, so you got your first answer, that is 2.71828. Okay, similarly next point t2, that is t1 plus h, that is 1.2. so y2, so y at 1.2, so this is just y1 plus hf t1 y1. so y1 is 0.271828, h is 0.1, so t1 is 1.1, y1 is 0.27828. so in the formula of f, replace t with 1.1. okay, in this here t with 1.1 and y with 0.271828, and finally you got this is 0.684756. okay, so I know solution at 1.1 and 1.2. now I come to second part. So say this is one initial point, I know solution y0, which is 0. Say this is 1.1, I know solution, that is 0.271828. Then next point 1.2, I know the solution 0.684756. Now it says that find solution at 1.04 using these values and use linear Lagrange interpolation. Okay, linear only. So you can check 1.04 will be somewhere here between 1 and 1.1. Okay, so use these values, okay, only to y0 and y1, and linear Lagrange interpolation to find value at this point. Okay, so recall the Lagrange interpolation that I have denoted by linear interpolation, that was L0x fx0 linear 1 degree plus L1x fx1. But here we have, in place of x we have t, So x is the point at which you want to compute solution. So x will be 1.04 and 0, x0 is starting point which is 1 and next point is 1.1, that is x1 in our notation. So in place of x we have t, okay, and in place of fx0 I have first value y0. So in place of fx0 we have y0 and y1. So in our notation we compute p1 at 1.04. So this is L0 at 1.04 multiplied by y0 and L1 at 1.04 multiplied by y1. Okay, so P1 at 1.04, that will be the approximate value of y at 1.04. Okay, so now write precisely values of L0. So L0 will be x minus x1 1.1 divided by x0 minus x1 multiplied by y0. So good thing is y0 is 0, so no need to write. And then L1 x minus, so in place of x we have t minus another 0.1 divided by 1.1 minus 1 multiplied by y1. So y1 is 0.271828. Okay, so this comes out approximately 0.108732. Okay, so and similarly you can find another value. And if in the same problem it says that use quadratic, and for quadratic you have to use all three values. Okay, value at 1, value at 1.1 and value at 1.2. Then you have L0 fx0 plus L1 fx1 plus L2 fx2. Three term will be there. Okay, and always remember that you can use interpolation to find values between two values. Okay, now take one example of modified Eulers. Also we have taken two examples of Eulers, and now take one example of modified Euler. So for initial value problem, dy by dt equal to t plus under root y with condition, initial condition. So for this IVP, find y at 0.2, find y 0.2 and y 0.4 with step size 0.2 and using modified Euler's method. So in standard notation I have dy by dt equal to t plus under root y. So this is my f, and y0 equal to 1 means t0 is 0 in the beginning and y0 is 1. Okay, so step size is 0.2. So you need to find solution at 0.2 and 0.4. So first point is t1, that is t0 plus h. So 0 plus 0.2, which is 0.2. Solution at this point is denoted by y1. Okay, and y1 will be y0 plus 1 by 2 k1 plus k2. So firstly I am writing k1 and k2. Okay, so what is k1? That is hf t0 y0. So this is 0.2 f t0 0 y0 is 1. So 0.2. So t plus under root y, under root 1 is 1. So this is 0.2. Similarly k2, that is hf t0 plus h. y naught plus k1. So this is 0.2. F at t naught plus h is just t1. So next point 0.2. y0 plus k1. So 1 plus 0.2. This is 1.2. Okay, so in the formula of ft plus under root y, under root 1.2. So this comes out k2 is approximately 0.2591. Okay, ft plus under root y. So now you have k1, k2. So substitute these values here, and solution at 0.2 is y0 plus 1 by 2 k1 plus k2. So 1 plus 1 by 2, k1 is 0.2 and k2 is 0.2591. So this is approximately 1.22955. Okay, so I started with 0 and solution at 0 is given 1, and solution at 0.2 I got 1.2295, and similarly you need to find solution at 0.4. So I'm just writing steps. So T2 will be T1 plus H, this is 0.4. Then again you calculate K1 and K2 at T1 Y1. Okay, and this will be T1 plus H, or you can write T2, so Y1 plus K1. So solution at 0.4 denoted by Y2, so this is Y0, this is Y1, and this will be Y2. So Y2 will be Y1 plus 1 by 2, these new K1 and K2. Okay, so just calculate all these values and fit here, and you can check. So this will be 0.2. So t plus under root y, t is 0.2, under root y is under root y1, so 1.22955. You can check with calculator. And second one will be, that will be k2. You can check with calculator. Okay, so that will be 0.2. So T1 plus H, so 0.4, and Y1 plus K1. Okay, so here you will get Y1 plus K1. So T plus under root Y. So just first calculate this one. Okay, so from this you can write second one, and then fit those values here. You got the solution at 0.4. Okay, so in that way you can write solutions. And you can write values if you want. So first value comes out 0.26177, and here you write that is approximately. So if you add y1 and k1, okay, and take square root, add 0.4, multiply with 0.2. So finally K2 comes out 0.64878, and now fit all values here. So approximate answer is 2.164538. So that is the solution of given initial value problem at 0.4. Okay, so in next lecture we will continue third and fourth order method.